Today, we embark on a journey where no one has gone before, beyond the boundaries of everything we know. We will explore spacecraft capable of flying on the energy of nuclear explosions. We will encounter hypothetical civilizations that can harvest the light of entire stars. And we will discover why the universe itself may have an expiration date. Friends, the universe is full of surprises. And today, we will take a step toward answering the ultimate question: can we ever leave the confines of our solar system? Right now, a spacecraft launched long before you were born is hurtling through utter darkness, 25 billion miles from Earth. It is the farthest distance any human creation has ever traveled. However, what will truly astound you is the fact that this probe will take 73,000 years to reach our nearest star. Imagine yourself standing on the shore of a boundless ocean, stretching beyond every conceivable horizon. You probably think our solar system ends at Pluto, but that's a misconception. Far beyond this distant icy world lies a region called the heliopause, where the sun's influence finally wanes. This invisible boundary is approximately 11 billion miles from our home. It is so far that sunlight takes 16 hours just to reach it. If you were to drive continuously in a car at highway speeds, this journey would take 12 million years. Imagine our solar system as a colossal soap bubble floating in boundless space. The sun inflates this bubble with what is called the solar wind, a stream of charged particles hurtling outward at over 1 million miles per hour. For billions of miles, this wind collides with the vacuum of space, forming a protective shield around everything we know. But eventually, even the sun's mighty breath loses its power. At the heliopause, our solar bubble meets the fierce winds of interstellar space. Here, alien particles from distant stars crash into our cosmic environment like waves breaking against a seawall. The temperature drops almost to absolute zero. The very atoms that compose space undergo changes. You have left the sphere of influence of the only star humanity has ever known. The Voyager 1 spacecraft crossed this boundary in 2012, becoming the first man-made object to enter true interstellar space. Its radio signals now take over 21 hours to reach Earth, longer than a full day. The probe sends us whispers from a realm so alien that our best scientists are still struggling to understand its meaning. But here's what should astound you. This edge, this boundary, which took us 35 years to reach with our fastest spacecraft, is less than 1/100,000th of the distance to our nearest neighboring star. Imagine taking one step on a journey that would circle the Earth 2.5 million times. That's how far we've come compared to how far we still have to go. The heliopause is not just a boundary, it's a warning. Beyond this point, the rules change entirely. The gentle warmth of our sun becomes meaningless. The magnetic fields that protect us from deadly radiation vanish. Even time itself behaves differently as you move between stars at unimaginable speeds. Standing on this cosmic shore, you realize that leaving our solar system is not just about building faster rockets or better technology. It means becoming something entirely new, a species capable of surviving in the vast, cold darkness between worlds. But our first visitors to this strange realm have already begun sending us the necessary secrets. Next, we follow humanity's boldest emissaries into the unknown. 2 golden records spin in the void, carrying the sounds of Earth to civilizations we may never meet. Launched in 1977, Voyager 1 and Voyager 2 were initially intended to explore Jupiter and Saturn, then quietly fade into space. Instead, they became humanity's first interstellar ambassadors, racing toward distant stars with messages from a blue planet they would never see again. Each probe carries a golden record containing sounds of whale songs, crying babies, and music from all corners of Earth, a cosmic message in a bottle. Voyager 1 travels at 38,000 miles per hour, faster than any spacecraft in history. At that speed, you could fly from New York to Los Angeles in 4 minutes. Yet, after 46 years of flight, it has barely begun its journey to the stars. The probe will not approach another star within spitting distance for 40,000 years. Imagine these spacecraft as medieval ships setting sail for unknown continents. Their captains knew they might never return, but they carried the hopes and dreams of all they left behind. The computer systems aboard the Voyager spacecraft possess significantly less computational power than a modern person's ordinary mobile phone. Nevertheless, they continue to function reliably in extremely hostile conditions, capable of instantly destroying any terrestrial equipment. The extreme cold in interstellar space doesn't just freeze material objects. It can alter the very atomic structure that makes up the spacecraft's components. Metal parts become brittle like glass. Electronic circuits, which have worked flawlessly for decades, begin to fail in unpredictable ways that their original engineers could never have foreseen. The probes are slowly fading as their nuclear power units weaken with each passing year. But these slowly fading emissaries of humanity have already revolutionized our understanding of what lies beyond the solar system. They have discovered magnetic fields distorted by powerful stellar winds into unimaginable shapes. They have measured cosmic rays emanating from explosions that destroyed entire galaxies before Earth even existed. The most astonishing discovery, however, is that interstellar space is not an absolute vacuum. It is filled with a thin soup of hydrogen atoms and mysterious particles left over from the birth of the universe. With each passing day, the radio signals transmitted by the Voyager spacecraft grow weaker. It is anticipated that by 2025, the probes will permanently cease operation as their nuclear power finally runs out. They will transform into silent ghost ships, drifting in the boundless ocean of stars, carrying our golden records to destinations we can only dream of for now. Astronomers hypothesize that in approximately 300 million years, when humanity has either evolved beyond recognition or completely vanished, one of these records may be discovered by an extraterrestrial civilization. They will be able to hear our music, our languages, our laughter. They will learn that once, on a small blue planet, a species existed that was brave enough to send messages in bottles into the immense cosmic ocean. However, Voyager has taught us a lesson even more significant than just knowledge of the far reaches of space. It has demonstrated that we can build machines durable enough to withstand interstellar travel. The true question is not whether we can reach other star systems. The question is whether we can live long enough to get there. And that brings us to the most terrifying discovery of all. Between our solar system and our nearest star stretches a darkness so profound that even Earth's deepest ocean trenches seem bright as daylight. Space is not just empty. It is aggressively and violently empty in ways the human mind struggles to comprehend. If our solar system were shrunk to the size where Earth was a common marble, the nearest star would be 1,400 meters away. This is equivalent to placing one marble in New York and hoping that with a perfect throw, you hit another marble located in Denver. But the emptiness extends far deeper than just vast distance. In the most advanced vacuum chambers on Earth, scientists can remove almost all air, leaving about 10 million particles per cubic centimeter. In interstellar space, however, there is less than 1 atom per cubic centimeter, and all the mass between the stars could fit into a volume smaller than a grain of sand. Imagine the following scenario. You are trying to swim through an ocean where the water is so sparse that you cannot feel it at all. It is so cold that your blood would freeze in seconds, and so permeated with invisible radiation that your DNA would be cooked from the inside, subjected to destructive effects. These are the conditions spacecraft face in the lifeless void between stars. This emptiness affects physics itself. Without air to transmit sound, the universe becomes perpetually silent. Without matter to conduct heat, the temperature hovers just above absolute zero at -267 degrees Celsius. At such extreme temperatures, even helium solidifies, metal crumbles like glass, electronics fail for reasons scientists are still trying to fully grasp. The radiation levels there make Chernobyl look like a health resort. Cosmic rays, particles accelerated by dying stars and black holes, slam into everything in their path at nearly the speed of light. A single cosmic ray carries more energy than a baseball thrown at 60 miles per hour, with all that energy concentrated in a space smaller than an atom. These invisible bullets, would tear apart human DNA, causing cancer, irreversible brain damage, and death within months. Even worse, the magnetic field that reliably protects us on Earth completely vanishes in interstellar space. Solar wind from distant stars generates electromagnetic storms that could disable any electronics we send there. Imagine trying to use your phone during a thunderstorm that lasts for centuries. However, perhaps the most unsettling discovery is that space is not uniform at all. Vast clouds of hydrogen gas, minuscule cosmic dust, and mysterious dark matter, whose existence we can detect but whose nature we still cannot comprehend, float between the stars. These giant clouds can span hundreds of light years, forming invisible barriers capable of severely damaging or even completely destroying any object crossing them at high speeds. Imagine flying through interstellar space at the speeds absolutely necessary to reach other stars. It would be akin to moving through a brutal sandstorm at 200 million miles per hour. In such conditions, every grain of sand transforms into a deadly bullet, and every gas cloud becomes an insurmountable wall of destruction. And yet, in some astonishing way, within this extremely hostile and boundless void, we have managed to discover something that fundamentally changes our entire perception of the possibilities of space travel. Our next presumed destination transforms this seeming emptiness into something filled with meaning. 4.25 light years from our planet shines a star so dim that a powerful telescope is required to observe it. Nevertheless, it holds the key to humanity's potential survival. Proxima Centauri is our nearest stellar neighbor, a red dwarf barely 1/8 the size of our Sun. If our Sun can be compared to a blazing bonfire, Proxima is more like a dying candle, flickering delicately in the cosmic wind. This miniature star emits so little light that its potentially habitable planet receives only 1% of the energy our Earth receives. But here's what truly sends chills down your spine. This planet, Proxima b, is in the so-called Goldilocks zone, where liquid water could very well exist. It is located just 4.25 light years away, which is practically next door by cosmic standards. At the speed of our fastest spacecraft, a journey to Proxima Centauri would take only 73,000 years. For an immortal species, this could be considered practically a weekend trip. Imagine Proxima Centauri as a distant lighthouse located on the opposite shore. You see its beam, you know exactly where it is, but the vast ocean separating you in safety is full of storms capable of destroying any ship you build. This star itself weighs only 12% of our Sun's mass. Nevertheless, it regularly erupts with solar flares that make our worst space weather seem absolutely mild. These stellar seizures release more energy in minutes than humanity has produced in its entire history. The flares bombard Proxima b with radiation levels that would sterilize its surface and completely destroy any atmosphere. If life exists there, it would either have to hide deep underground or develop protective mechanisms that would make our best technologies seem like paper armor. Red dwarfs like Proxima live for trillions of years, hundreds of times longer than our Sun. While our solar system will cease to exist in 5 billion years, Proxima Centauri will still be burning when the universe itself becomes cold and dark. This is the ultimate long-term goal for a species planning to outlive the death of stars. However, the journey to it presents the greatest challenge humans have ever faced. Traveling at 10% the speed of light, much faster than anything we have ever created, would still take 43 years, an entire human lifetime spent crossing the void between worlds. Babies born aboard such a ship would grow old and die without ever seeing their destination. The energy required to achieve such colossal speeds defies human imagination. You would need to convert matter directly into energy using Einstein's famous equation. The fuel alone would weigh more than entire mountains. Even if we successfully solve the energy problem, cosmic radiation over decades of flight would be absolutely lethal to any human crew. Nevertheless, scientists have already discovered dozens of potentially habitable planets around red dwarfs within 50 light years of Earth. These ancient suns offer humanity something our own star cannot: time. billions of years to evolve, explore, and spread throughout the galaxy before the last stars extinguish. Proxima Centauri is not just our closest neighbor, it is our cosmic insurance policy. But reaching it requires us to break the most fundamental speed limit in the universe, and this is where Einstein's rules turn everything upside down. Nothing with any mass can ever reach the ultimate speed of light, and this fundamental fact could doom humanity to eternal existence within a single planetary system. The great Albert Einstein, a keen genius, discovered that as an object approaches the speed of light, something seemingly impossible occurs. Its mass increases infinitely. To accelerate even a single atom to the light barrier would require all the energy contained within the universe. This is not just incredibly difficult, it is mathematically impossible, a fundamental limitation woven into the very fabric of reality, like a cosmic speed limit imposed by the laws of physics themselves. Light travels at an astonishing speed, 671 million miles per hour. At this dizzying pace, you could circle the Earth 7.5 times in just 1 second. Reaching the moon would take only 1.3 seconds. Crossing our entire vast solar system could be done in 11 hours. Nevertheless, even at this incredible speed, reaching Proxima Centauri, our nearest star, would take 4.25 years. Imagine the speed of light as a strict speed limit on a cosmic highway. Except the penalty for trying to break it is not just a fine. It is the complete destruction of physics as we know and understand it. As a spacecraft approaches the speed of light, time itself begins to slow down relative to the rest of the universe. At 99%, the speed of light, 1 year spent on your ship equals 7 years on Earth. This phenomenon gives rise to what scientists call the time dilation paradox. A crew traveling to Proxima Centauri at near light speed might experience only a few months of flight time, while everyone they left behind would age by decades. They would return to find their friends and family dead and their civilization changed beyond recognition. They would become time travelers, trapped in a future they never chose for themselves. However, energy requirements make even this scenario impossible with current technology. To accelerate a spacecraft weighing as much as the space shuttle to just 10%, the speed of light would require the energy output of all the United States for over 100 years. Achieving 90% the speed of light would demand more energy than our sun produces in an entire century. Even if we solve the energy problem, relativistic effects would turn harmless space dust into deadly cosmic bullets. At near-light speeds, a grain of sand would hit with the force comparable to a nuclear weapon. The sparse gas between stars would transform into a wall of radiation that would vaporize any known material. The universe itself becomes hostile and dangerous for high-speed travel. And yet, Einstein's equations also revealed something unusual. While nothing can move faster than light through space, space itself can expand faster than light. The universe has been doing precisely that since the Big Bang. During cosmic inflation, regions of space separated faster than light could travel between them. This kind of loophole in Einstein's laws opens the door to what sounds like pure science fiction. We may not need to travel faster than light if we can convince space itself to move us. Instead of breaking the cosmic speed limit, we could ride the expansion of space-time itself. But harnessing this power requires technology so advanced it might seem like magic. Our first attempt to outsmart Einstein uses the most powerful force in the universe. Imagine yourself surfing a wave of nuclear explosions. Each explosion is powerful enough to level an entire city. Project Orion, conceived in the 1950s, proposed the most audacious spacecraft design in human history, a vessel propelled by detonating atomic bombs behind a massive steel plate. Every few seconds, another nuclear weapon would explode, pushing the ship forward with forces that would turn ordinary materials to powder. The physics does work. Nuclear explosions release more energy per pound than any other known reaction. A single atomic bomb contains enough energy to power New York City for 2 weeks. Combine thousands of such explosions, and you could accelerate a massive spacecraft to 5% the speed of light, fast enough to reach Proxima Centauri in less than 100 years. Imagine it as the ultimate motorcycle, only instead of burning gasoline, you detonate hydrogen bombs every 3 seconds and ride the shockwave. The spacecraft would require shock absorbers the size of buildings and a pusher plate made of materials capable of withstanding multiple nuclear blasts. Engineers calculated that such a ship could weigh thousands of tons, yet achieve speeds chemical rockets could only dream of. The original Project Orion design included a crew compartment securely protected by numerous layers of lead shielding. Inside this vessel, astronauts would experience brief moments of crushing acceleration, followed by periods of complete weightlessness as the ship moved from one nuclear explosion to the next. This unique journey could be compared to moving inside a giant hammer, constantly shaken by the blows of an angry deity's mighty fist. However, despite such protection, radiation exposure would remain deadly. Each nuclear pulse would inevitably flood the spacecraft with powerful gamma rays, neutron fluxes, and a multitude of radioactive particles. Even with the most robust shielding, crew members would receive radiation doses capable of causing severe illnesses such as cancer, infertility, and ultimately, death. Furthermore, the ship itself would eventually become so radioactive that any approach without specialized protection would be tantamount to suicide. Modern modifications of the pulse propulsion engine propose using nuclear fusion instead of atomic fission, allowing for cleaner explosions with significantly less radioactive fallout. Thermonuclear bombs function by combining hydrogen atoms, releasing energy directly from Einstein's famous equation, and producing mostly harmless helium as waste. These fusion pulses could potentially accelerate a spacecraft to 1/10 the speed of light, significantly reducing radiation exposure to levels compatible with survival. Nevertheless, the engineering challenges facing the creators of such a craft remain truly astonishing. The pusher plate, a key structural element, would have to withstand temperatures in the millions of degrees and pressures significantly exceeding those at the Earth's core. The shock absorbers, designed to absorb impact loads, would have to compress and expand like cosmic springs, each larger than a skyscraper. Storing the fuel alone would require a repository capable of safely containing thousands of nuclear warheads. Despite all these complexities, computer simulations demonstrate that a nuclear pulse propulsion engine could indeed function using technologies we already understand today. Unlike concepts requiring exotic physics or still theoretical particles, this idea only needs engineering solutions for known problems. We could build an Orion-style spacecraft within 50 years if appropriate resources were allocated. The true obstacle here is not technical, it is purely political. Building a nuclear weapon-propelled spacecraft would require international cooperation on a scale never before achieved. Such a ship would, in essence, be a flying nuclear arsenal, potentially capable of destroying entire planets. However, if we are serious about reaching the stars, we may have to ride the tiger. Next, we turn to a gentler approach, harnessing the universe's own energy. Through the vacuum of space flows an invisible river of pure energy, and humanity is finally learning to swim in it. Light itself, as is known, possesses momentum. Every photon hitting a surface imparts a tiny push, like cosmic raindrops striking a window pane. This force is incredibly weak. The pressure of sunlight on Earth is equivalent to the weight of an ordinary paperclip distributed over a football field. However, in the airless void of space, even this gentle touch can accelerate a spacecraft to truly incredible speeds. Solar sails operate on a principle inverse to that of sailboats. Instead of catching wind to move across water, they catch starlight to move through space. The sail itself must be extremely thin, thinner than soap bubbles, lighter than butterfly wings, yet strong enough to withstand a long journey between worlds. Imagine wrapping a spacecraft in aluminum foil so thin it could be torn by a single breath. The Japanese probe Icaros convincingly demonstrated the practical feasibility of a solar sail. Launched in 2010, this experimental craft deployed a sail the size of a basketball court and successfully maneuvered in space using only photon pressure. The sail's thickness was only 7.5 thousandths of an inch. It was so thin that 14,000 sheets stacked together would equal the thickness of a human hair. But what makes solar sails truly exciting is that they never run out of fuel. Chemical rockets burn their fuel in minutes and then coast. Nuclear rockets require vast amounts of radioactive material. Solar sails, however, accelerate continuously as long as starlight falls on them, gaining speed over months and even years until they move faster than any rocket ever built. Project Breakthrough. Starshot harbors plans to apply this fundamental principle to reach the Proxima Centauri star system within 20 years. Instead of relying solely on sunlight, the project initiators intend to use the most powerful lasers ever created by humanity to propel miniature spacecraft. A ground-based laser array, capable of generating 100 billion watts of energy, will focus its beam on sails comparable in size to postage stamps, accelerating them to 20% of the speed of light in just 2 minutes. These star chips will weigh less than a paperclip but carry cameras, computers, and reliable communication equipment, racing through interstellar space at 134 million miles per hour. They could take detailed photographs of planets orbiting Proxima Centauri and transmit these images back to Earth. A journey that would take Voyager 73,000 years could, in this case, be completed in just 20 years. However, scaling solar sails for crewed missions presents a host of challenges that far exceed current engineering capabilities. A sail large enough to carry humans would have to be hundreds of miles across, exceeding the size of most countries. Maintaining the integrity of such a colossal structure while accelerating to high speeds would be comparable to trying to keep a spiderweb intact during a raging hurricane. Furthermore, the sails would have to withstand continuous bombardment by cosmic dust, radiation, and the intense laser light propelling them forward. At the temperatures generated by such powerful beams, most known materials would instantly vaporize. Therefore, engineers are actively experimenting with metamaterials, artificially created substances with unique properties not found in nature. Solar sails offer humanity something no other propulsion system can: the unique ability to harness the fundamental forces of the universe itself. We are not fighting the laws of physics. On the contrary, we are learning to interact with them harmoniously. But what if we could not only capture starlight? What if we could consume the universe itself as fuel? Imagine a spacecraft that feeds like a cosmic whale, collecting hydrogen atoms from the abyssal void and transforming them into the hottest fire in the entire universe. The Bussard ramjet, a concept proposed by physicist Robert Bussard in 1960, is one of the most elegant solutions for interstellar travel ever conceived by the human mind. Instead of carrying a fuel supply, the spacecraft would collect hydrogen atoms directly from space itself, using a powerful magnetic field stretching for thousands of miles. These atoms would then be compressed and fused, releasing the energy needed to propel the ship forward. Space is not absolutely empty. Even in the immense darkness between stars, there's approximately 1 hydrogen atom per cubic inch. This seems like a minuscule amount. However, at high speeds, these atoms accumulate quickly. A ramjet moving at 10% the speed of light would collect billions of atoms every second, providing a continuous supply of fusion fuel. Imagine it as a cosmic jet engine that breathes space instead of ordinary air. Jet engines function by compressing air, mixing it with fuel, and then igniting this mixture to create thrust. A fusion ramjet, in turn, would compress hydrogen from space, fuse it into helium, and use the released energy for even greater acceleration. The faster it moves, the more fuel it collects, creating a unique feedback loop that could theoretically allow it to achieve significant fractions of the speed of light. The required magnetic field would be colossal, surpassing the size of Earth itself. This invisible net would have to be powerful enough to capture individual atoms moving at relativistic speeds, yet precise enough to guide them into a fusion reactor without loss of efficiency. Engineers compare this task to trying to catch raindrops with a net while riding a motorcycle at 200 miles per hour. The fusion reactor itself would operate at temperatures of 100 million degrees, 6 times hotter than the sun's core. At such extreme temperatures, hydrogen nuclei overcome their natural mutual repulsion and fuse, converting a small amount of mass directly into energy according to Einstein's famous equation. The reaction produces no radioactive waste, only helium and pure energy. However, the fusion ramjet faces a truly cruel paradox that calls into question its practical feasibility. To begin functioning effectively by collecting enough fuel, it needs to develop an extremely high initial velocity. Achieving this critical threshold requires the use of traditional rocket engines or other existing propulsion systems. This can be compared to trying to push-start a car that is only capable of moving at highway speeds, which is an inherently impractical approach. Computer simulations have also revealed another serious problem. As the ramjet approaches higher speeds, the hydrogen atoms it is supposed to collect as fuel begin to behave completely differently. Instead of serving as an energy source, they turn into a form of radiation. When the spacecraft's speed reaches approximately 20% of the speed of light, this fuel becomes so high energy that it actually starts to slow the spacecraft down instead of accelerating it. Thus, the ramjet encounters an invisible wall built from the very atoms it initially sought to consume. Recent developments offer a potential solution to this fundamental problem. They propose using a powerful magnetic field not only to effectively collect hydrogen fuel, but also to compress space itself around the spacecraft. This innovative approach aims to create a region of increased hydrogen density while simultaneously minimizing the relativistic effects that previously turned valuable fuel into useless radiation. As a result, the ship would essentially glide through space, enclosed within its own magnetic bubble. If humanity could build a functioning fusion ramjet, it would be the ultimate expression of the living off the land concept in deep space. The spacecraft would transform into a fully self-sustaining ecosystem, drawing energy from the universe itself and capable of delivering human consciousness to distant stars. However, even this elegant solution pales in comparison to an idea that radically rewrites all the rules of space travel. What if we didn't have to move at all and instead convinced the universe to deliver us to our destination? Mexican physicist Miguel Alcubierre discovered something truly extraordinary in Einstein's equations. While no object can move faster than light through space, there is no fundamental limit to how fast space itself can move. His solution sounds like pure magic. Compress space directly in front of your spacecraft while expanding it behind, thereby creating a wave that carries you faster than light without actually accelerating the object. Imagine it like standing on a moving walkway at an airport. You aren't walking faster than usual, but the walkway itself carries you forward at high speed. An Alcubierre drive would create a similar effect with space-time itself, forming a bubble within which the ship never actually exceeds the speed of light relative to local space. Inside this so-called warp bubble, you would experience neither the destructive forces of acceleration, nor time dilation, nor the lethal radiation that usually accompanies high-speed travel. A journey to Proxima Centauri, for example, could take just a few days instead of decades. You could travel to the far reaches of the galaxy and return home to find that only years, not millennia, had passed on Earth. The mathematics of this idea worked flawlessly. Einstein's field equations allow for solutions where space curves so strongly that it creates a kind of bridge connecting separate regions of spacetime. These hypothetical tunnels, known as wormholes, could theoretically link places separated by billions of light years, or even connect our universe to entirely different universes with their own unique laws of physics. Imagine spacetime as a stretched rubber sheet with marbles rolling across its surface. Massive objects like stars and black holes create dents and curves in this sheet. A wormhole would be like a tube connecting 2 points on the sheet, allowing a marble to instantly travel from one place to another without rolling across the surface. However, naturally occurring wormholes, if they exist at all, would be smaller than atomic nuclei and would collapse in fractions of a second. Creating a stable wormhole large enough for a spacecraft to pass through would require what is known as exotic matter with negative energy density, the same theoretical substance needed for Alcubierre drives to function. This material would have to violate energy conditions that may be fundamental to our universe. Even if humanity could successfully stabilize a wormhole, traveling through it might prove far more dangerous than beneficial. The intense gravitational fields present at the entrance of such a space-time tunnel would have the potential to stretch travelers like taffy. in a process scientists call spaghettification. The tidal forces arising in such conditions could affect a person's head and feet in different directions with enough power to tear apart the atoms that make up their body. The energy requirements for creating traversable wormholes make even the most powerful antimatter engines seem quite modest by comparison. Current scientific estimates indicate that stabilizing a wormhole just 3 feet wide would require negative energy equivalent to the mass of the planet Jupiter. Creating an entire network of wormholes capable of connecting nearby star systems would require energy sources comparable in scale to entire galaxies. Some modern theories suggest that microscopic wormholes are constantly appearing and disappearing at the quantum level, forming a kind of foam-like structure in the very fabric of space-time. It is possible that advanced civilizations could master methods of capturing and enlarging these quantum wormholes, transforming them into macroscopic transport networks for movement in the universe. Time travel adds another layer of complexity to the physics of wormholes. A sufficiently advanced civilization could potentially be capable of creating closed time-like curves, special paths through spacetime that return to earlier moments. This could provide the possibility of communicating with the past, or even traveling back in time, which, in turn, would create paradoxes capable of threatening the very fabric of causality. Alternatively, wormholes could represent one-way passages, allowing matter and energy to travel in only one direction. Such structures could serve as cosmic waste disposal systems, channeling waste matter and energy from one universe to another. Advanced civilizations might use such formations to manage large-scale engineering projects. Recent scientific research indicates that quantum entanglement, the mysterious connection between paired particles, may be closely related to the physics of wormholes. If this assumption proves true, this discovery could lead to entirely new approaches for creating artificial wormholes, using quantum mechanical effects rather than exotic matter, as previously believed. The search for natural wormholes continues with active use of gravitational wave detectors and space telescopes. If humanity discovers even one stable wormhole, this event will revolutionize our understanding of physics and potentially provide humans access to the entire universe. However, before we can build cosmic subway systems, we may need to become true masters of the energy of our own stars. Imagine the ability to capture every photon of energy emanating from our sun, transforming our star into a giant cosmic power plant capable of fueling galaxy-altering projects. The Dyson sphere, a concept developed by physicist Freeman Dyson, represents the ultimate expression of stellar engineering, a megastructure that completely surrounds a star to collect all its energy output. Such a structure could collect billions of times more energy than humanity currently uses, providing enough power for truly cosmic projects. Our sun produces approximately 400 trillion watts of energy every second. Yet, Earth intercepts only 1/1000th of this energy, while the rest is uselessly radiated into space. A complete Dyson sphere would capture virtually all of this energy, providing enough power for quintillions of Earth civilizations to function simultaneously. Imagine building a shell around the sun at roughly Earth's orbital distance, creating an artificial world with a surface area hundreds of millions of times that of Earth. The inner surface of such a sphere could be covered with solar collectors, habitats for trillions of people, or massive computer systems managing digital civilizations. However, constructing such a megastructure would require dismantling entire planets for the necessary raw materials. For example, Mercury, the innermost planet of our solar system, contains approximately enough material to build a Dyson sphere 1 meter thick. The construction project would take thousands of years and require self-replicating robots working continuously at speeds that make our fastest manufacturing seem glacial. A solid, monolithic Dyson sphere, a single shell around a star, would prove gravitationally unstable, and its construction is practically unfeasible. Such a structure would require materials whose strength surpassed any known to modern science, and it would somehow have to maintain its fixed position relative to the sun. As a more realistic alternative, engineers propose the concept of Dyson swarms. millions of autonomous solar collectors that would orbit the central star in extremely complex trajectories designed for maximum energy collection. Each of these collectors in the swarm could reach the size of an entire continent, and they would be positioned at carefully calculated distances to prevent collisions while maintaining optimal efficiency in converting starlight. From the outside, such a swarm would appear as a dimming star surrounded by excess infrared radiation, as the collectors would actively convert starlight into usable energy. Advanced versions of Dyson spheres could include rotating habitable sections with artificial gravity, giant computer systems for managing uploaded consciousnesses, and vast industrial complexes designed to build even grander megastructures. Such a sphere could support quadrillions of inhabitants while simultaneously enabling large-scale interstellar exploration and colonization missions. Some astronomers are actively searching for signs of alien Dyson spheres, carefully observing stars that periodically dim or emit unusually large amounts of infrared radiation. Such unique signatures could indicate the presence of highly advanced civilizations that have already mastered stellar engineering technologies. In particular, the star Caic 8468852 exhibited mysterious dimming patterns that briefly caused significant excitement among researchers before more mundane explanations were found. The creation of a Dyson sphere would mark a fundamental transition for humanity from a planetary species to a stellar civilization. We would cease to depend on the limited resources of individual worlds, gaining the ability to directly utilize the fundamental energy source that powers all life in our solar system. The energy obtained from a Dyson sphere could enable projects beyond modern imagination, moving entire planets, accelerating massive generation ships to significant fractions of the speed of light, or even attempting to modify the sun itself to extend its lifespan. Such capabilities would place humanity on par with cosmic civilizations capable of reshaping the universe itself. However, mastering stellar energy is only the initial stage of cosmic engineering. Advanced civilizations can reach levels of power that eclipse even the energy output of entire stars. Across the cosmos, there may exist civilizations so advanced that they harvest the energy of entire galaxies, treating stars as we humans treat simple campfires. The Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev, is a classification system for civilizations based on their energy consumption level. Type 1 civilizations use all the energy available on their home planet. Type 2 civilizations capture all the energy of their star. Type 3 civilizations manage the energy of their entire galaxy, which is approximately 10 billion times more energy than a Type 2 civilization. Humanity is currently at approximately 0.7 on this scale. We use only a tiny fraction of the energy sources available on Earth and have barely begun to directly harness solar energy. Our entire civilization consumes less energy than our planet receives from the sun in just 1 hour. Imagine this scale as comparing a candle flame to a bonfire, and then to a wildfire engulfing entire continents. Each successive level represents a billion or trillion-fold increase in power. A Type 3 civilization would have access to such vast levels of energy that it could restructure matter on galactic scales. Type 2 civilizations would likely build Dyson spheres or similar megastructures around their stars. They could move planets into optimal positions, extend stellar lifespans through stellar engineering, or even create artificial stars from accumulated gas and dust. Their grand projects would be visible from other galaxies as unusual modifications to star systems. Type 3 civilizations would view entire star systems as nothing more than building materials for their grand designs. They would likely be capable of constructing galactic computers using the colossal multitude of positions and movements of billions of stars as elementary components for information processing. Potentially, they could redirect the trajectories of stellar streams, alter the rotation of entire galaxies, or even prevent catastrophic galactic collisions by skillfully applying gravitational engineering. Such highly advanced civilizations could shed light on some of the most mysterious phenomena we observe in the depths of space. For example, the enigmatic dark matter might simply be a signature of Type 3 civilization engineering projects. Powerful gamma-ray bursts, in turn, could represent the exhaust gases of giant stellar engines. And the Great Attractor, that colossal gravitational anomaly that pulls entire galaxies towards it, could very well be evidence of large-scale cosmic construction. The energy available to Type 3 civilizations would be so immense that it would suffice for projects that currently seem like pure fantasy. They could potentially create new universes, alter the fundamental constants of physics, or build structures exceeding the size of galaxy clusters. Perhaps they would even be able to survive the heat death of the universe, transferring energy between cosmic epochs. Some scientists even hypothesize the existence of Type 4 civilizations, which utilize the energy of the entire observable universe. Such beings would exist on such immense scales that individual galaxies would be like cells in their colossal cosmic body. They might be indistinguishable from the fundamental forces of nature themselves. The Fermi paradox asks, why have we not yet encountered any advanced alien civilization, despite the staggering number of stars and planets in our galaxy? One possible hypothesis is that Type 2 and Type 3 civilizations exist, but their activities occur on such grand scales that we are simply unable to recognize them as artificial. Alternatively, these civilizations may deliberately avoid interfering with primitive species like ours. A Type 3 civilization would likely view humanity much as we view bacteria, perhaps interesting to study, but not worthy of direct communication. It is entirely possible that we live within some kind of cosmic preserve maintained by beings whose thoughts operate on galactic timescales. Achieving Type 1 civilization status could be a crucial milestone in human history. Once we learn to harness the full energy potential of our planet through fusion power, space-based solar collection, and efficient global distribution, we can embark on projects that will lead to interstellar expansion and subsequent stellar engineering. However, the path to cosmic civilization raises uncomfortable questions about our current cosmic isolation. In a galaxy containing 400 billion stars and potentially trillions of planets, why does the cosmic ocean seem so eerily silent? The Fermi paradox, named after the eminent physicist Enrico Fermi, highlights the profound contradiction between the high probability of extraterrestrial life and the complete absence of any convincing evidence for advanced civilizations. Given the immense age of the universe and the rapid pace of technological development, alien civilizations should have had enough time to colonize the entire galaxy many times over. Consider the mathematical calculations. Our galaxy has a diameter of approximately 100,000 light-years and is 13.6 billion years old. A civilization expanding at just 1% the speed of light could colonize every star system in the galaxy within 10 million years, which is less than 0.1% of the galaxy's total age. Imagine this as a drop of ink released into a glass of water. The ink quickly spreads until it fills the entire glass. Similarly, any technological civilization should spread throughout the galaxy like a wave, leaving undeniable traces of its presence everywhere. Nevertheless, we see nothing. No colossal megastructures, no radio signals, no evidence of stellar engineering or large-scale cosmic construction projects. The Drake equation attempts to estimate the number of communicating civilizations in our galaxy by multiplying factors such as the rate of star formation, the fraction of stars with planets, and the probability that life will develop intelligence. Even the most conservative estimates suggest that thousands of advanced civilizations should exist in our galaxy. But the universe, at first glance, seems suspiciously uninhabited. The cosmic microwave background radiation, an echo of the Big Bang, shows absolutely no signs of having been modified by highly advanced extraterrestrial civilizations. None of the countless stars exhibit the characteristic dimming patterns that could be caused by giant engineering structures known as Dyson spheres. Nor are there any specific gamma-ray signatures that might indicate the operation of engines using antimatter. The galaxy, to all outward appearances, seems completely untouched by intelligence, with the exception, of course, of one tiny blue planet located in a completely unremarkable solar system. Several possible explanations for this pervasive cosmic silence have been put forward. The Great Filter hypothesis suggests the existence of some obstacle or series of obstacles that prevent life from reaching the stage of an advanced technological civilization. This filter could be located in the earliest stages, such as the origin of life itself, or in later stages, such as the development of complex cells, the evolution of intelligence, or the transition to active space expansion. Perhaps most unsettling is the suggestion that the Great Filter is yet to be passed by humanity. Advanced civilizations may be inevitably doomed to self-destruction as a result of global nuclear conflicts, catastrophic ecological collapse, uncontrolled development of artificial intelligence, or other technological disasters before they can expand their presence beyond their home planetary systems. As an alternative explanation, it is entirely possible that highly advanced extraterrestrial civilizations are deliberately concealing their presence. They could be using advanced stealth technologies that render their activities completely invisible to our still primitive sensors, or they could be operating in dimensions or energy spectra that humanity has not yet learned to detect. It is not impossible that they are already present in our solar system right now, carefully observing humanity from places we would never think to explore. The zoo hypothesis, in turn, suggests that planet Earth exists in a kind of cosmic preserve maintained by highly advanced civilizations. These aliens could have an agreement not to interfere with primitive species like ours while they go about their business on scales that are too vast for us to comprehend. Some scientists also suggest that intelligence, as it develops, naturally turns inward rather than outward. Instead of building giant starships and megastructures, advanced civilizations may focus on creating increasingly complex virtual realities or uploading their consciousnesses into compact computer systems that require minimal energy to function. The recent discovery of potentially habitable exoplanets makes this paradox even more mysterious and intriguing. We now know that Earth-like worlds are quite common throughout the galaxy. The raw materials necessary for the emergence of life and the development of intelligence appear to be everywhere. Nevertheless, the products of that intelligence are stubbornly absent from our observations. Perhaps humanity is looking in the wrong places or asking the wrong questions. Advanced civilizations may communicate using quantum entanglement, gravitational waves, or other phenomena that we are only beginning to understand. Their presence may become apparent once we develop the right tools to detect it. The answer to the Fermi paradox will fundamentally shape humanity's cosmic future. If we prove to be alone in this vast universe, then a tremendous responsibility falls upon us to spread life and intelligence throughout this seemingly empty cosmos. If we are not alone, then we must prepare for potential contact with intelligences that may be as far removed from us in their development as we are from the simplest bacteria. In either case, the search continues, and the implications grow deeper with each silent year. Life may be the universe's greatest hitchhiker, spreading from world to world on cosmic winds and traveling on meteorites through the boundless darkness between stars. Panspermia, the theory that life spreads throughout the universe via comets, asteroids, and other celestial bodies, offers a radical explanation for how biology conquers space. Instead of arising independently on each world, life may have had a single common ancestor that traveled between planets, seeding the galaxy with the building blocks of consciousness. We know that rocks regularly move between planets in our solar system. Meteorite impacts on Mars's surface eject debris into space, some of which eventually falls to Earth as Martian meteorites. Scientists have found over 200 confirmed rocks from Mars in Earth collections, proving that natural processes can transport material millions of miles in space. Imagine these meteorites as interplanetary spore capsules, transporting microscopic passengers on journeys spanning millions of years. The deep vacuum of space creates ideal conditions for preserving organic structures. The absence of oxygen prevents decomposition, and the lack of water prevents complex organic compounds from breaking down. Moreover, radiation levels, contrary to popular belief, can actually aid in the preservation of biological materials through a phenomenon known as radiation-induced polymerization. Some types of bacteria and other microorganisms exhibit astonishing resilience to the extremely harsh conditions of space. For example, tardigrades, these microscopic animals also known as water bears, can survive for decades in the airless vacuum of space, enduring radiation levels that would instantly kill a human. After rehydration, they resume their normal activities as if nothing unusual had happened. Numerous experiments conducted on the International Space Station have exposed various microorganisms to the space environment for extended periods. Many not only survived, but even proliferated faster in microgravity conditions. These impressive discoveries suggest that life is potentially capable of surviving interplanetary journeys that can last for months or even years. However, interstellar panspermia presents far more serious and large-scale challenges. Traveling between different star systems takes millions of years, even for objects moving at the maximum possible speed. Cosmic radiation, extremely low or high temperatures, and simply the inevitable passage of time would put any biological preservation system to the ultimate test. Some researchers hypothesize that life spreads not as living organisms, but in the form of complex organic molecules that serve as templates or matrices for the genesis of new life on suitable worlds. These molecular blueprints could survive long interstellar journeys, retaining enough information to kickstart evolutionary processes on planets with favorable conditions. The concept of directed panspermia suggests that highly advanced civilizations intentionally spread life throughout the galaxy, launching biological payloads toward star systems that appear promising for habitation. These alien gardeners could use self-replicating probes to disseminate genetic material, thereby creating a vast galactic network of interconnected biospheres. If the theory of panspermia is true, it could explain the apparent speed with which life appeared on early Earth. Instead of requiring billions of years to evolve from scratch, Earth life could have received a kind of head start, provided by genetic material from older civilizations. This theory also instills hope for finding life in other parts of our solar system. If Earth life originated from interplanetary exchange, then objects like Mars, Europa, Enceladus, and other worlds may very well contain organisms related to Earth biology. We might discover that we have cosmic cousins living beneath the ice of Jupiter's moons. Advanced civilizations could use directed panspermia as a form of cosmic insurance, spreading their genetic heritage across thousands of worlds to ensure the survival of their species, even if their home planet is destroyed. In this way, the galaxy could be filled with descendants of long-gone civilizations whose biological legacy would be preserved in the genes of countless species. DNA analysis of extremophile organisms on Earth sometimes reveals genetic sequences that seem too complex to have evolved solely in terrestrial conditions. These biological signatures could be a kind of echo of our cosmic origins, genetic postcards from civilizations that seeded our world billions of years ago. If humanity ever develops the technology to seed other worlds with life, we will continue a process that may be as old as the galaxy itself. We could become cosmic gardeners, spreading Earth's genetic richness to sterile worlds throughout our local neighborhood. However, successful galactic gardening requires a careful search for suitable neighborhoods for planting. Not all areas in our galaxy are safe for life, and choosing the wrong address can mean the difference between thriving and perishing in the boundless cosmic wasteland. Just as planets possess specific habitable zones around their stars where liquid water can exist, galaxies also have their unique regions favorable for the emergence and sustained existence of complex life. If a star system is located too close to the galactic center, the deadly radiation emanating from massive black holes and grandiose supernova explosions can completely sterilize entire regions. Conversely, in the too distant outer reaches of space, there's an insufficient quantity of heavy chemical elements necessary for the formation of planets capable of supporting life. Our solar system is in a region astronomers call the galactic Goldilocks zone, approximately 26,000 light-years from the center of the Milky Way. This seemingly unremarkable location provides an ideal balance of safety and access to vital resources, which has been critical for billions of years of stable evolution. Imagine the galaxy as a vast cosmic metropolis with diverse neighborhoods. The central part, surrounding a supermassive black hole, is densely populated with ancient stars where supernova explosions frequently occur, and radiation levels are such that they would boil any planet. The outer suburbs, however, suffer from an acute shortage of heavy elements needed to form rocky worlds. But the middle regions, the very suburbs where we reside, offer an optimal combination of safety and all necessary amenities. The galactic center hosts a supermassive black hole 4 million times the mass of our Sun. This cosmic monster occasionally devours nearby stars and gas clouds, generating powerful jets of high-energy particles that extend for thousands of light years. Any civilization unlucky enough to be caught in these cosmic spotlights would be sterilized by radiation doses millions of times exceeding lethal levels. Active star formation in the galactic core creates a kind of stellar nursery where massive stars rapidly live out their lives and die young in spectacular supernova explosions. These stellar death throes release gamma rays and cosmic particles that would destroy planetary atmospheres and the complex chemistry needed to sustain life. However, the outer regions of the galaxy present their own unique challenges. Stars in the galactic halo formed when the universe was still very young and contained almost exclusively elements lighter than hydrogen and helium. These metal-poor stars are unable to form rocky planets or support the complex chemistry required for carbon-based life. Earth is in a cosmically fortunate location where star formation has been active enough to produce heavy elements through stellar nucleosynthesis, but not so active that frequent supernova explosions make the vicinity uninhabitable. Our region has experienced relatively few galaxy-scale catastrophes over the past 4 billion years. The galactic habitable zone is not static. It constantly changes over time as star formation rates vary, and the abundance of heavy elements evolves in different regions. Areas uninhabitable today may very well become prime real estate in 1 billion years, while currently safe regions may turn into cosmic dead zones. Recent scientific research indicates that spiral arms can play a crucial role in galactic habitability. These grandiose structures trigger waves of star formation that can disrupt planetary systems through gravitational perturbations, but they also concentrate the heavy elements necessary for the formation of rocky planets. Our solar system appears to have a fortunate orbital pattern that keeps it mostly between the spiral arms, allowing it to avoid the worst effects of these stellar traffic jams while benefiting from their element-enriching effects. Advanced civilizations could deliberately choose star systems in optimal galactic locations for their long-term expansion efforts. They might wait for spiral arm passages before establishing colonies or use stellar engineering to move their entire solar systems to safer regions. As we plan humanity's expansion beyond Earth, understanding galactic habitable zones will be crucial for selecting target destinations. We want to invest our limited resources in star systems that offer billions of years of stable conditions for human civilization to thrive. But even in the safest galactic neighborhoods, some stars offer better long-term prospects than others. While our Sun will die in 5 billion years, there are stars so frugal with their fuel that they will continue to shine for trillions of years, longer than the current universe. The current universe represents red dwarfs, being the most miniature and coolest stars in our galaxy, represent humanity's best chance for true long-term existence. These cosmic Scrooges consume hydrogen so slowly and efficiently that they will continue to generate energy long after larger stars, including our Sun, exhaust their fuel and cease to exist. Stars like Proxima Centauri, our nearest cosmic neighbor, have a mass of only about 12% of the Sun's mass, yet their lifespan is approximately 1,000 times longer than the Sun's. While our Sun may have about 5 billion years of stable hydrogen burning left, red dwarfs will continue to shine for 6 to 12 trillion years. This is more than enough time for evolution to restart from bacteria and give rise to entirely new forms of intelligent life. Imagine red dwarfs as hybrid cars compared to gas-guzzling trucks. They burn their fuel so efficiently that even the smallest red dwarf will outlive every other type of star in the galaxy. When the last massive stars explode as supernovae and medium-sized stars shed their outer layers, red dwarfs will still be quietly converting hydrogen into helium. The galaxy contains approximately 75% red dwarfs, making them by far the most common stellar type. Within 50 light-years of us, there are over 100 red dwarfs, many of which likely have planetary systems. These dim stars offer humanity hundreds of potential directions for interstellar colonization. However, life around a red dwarf requires adaptations that would fundamentally change human civilization. These stars produce only a fraction of our sun's energy output, meaning that habitable planets must orbit much closer to remain warm enough for liquid water to exist. A planet in the habitable zone around a red dwarf might have an orbital period of only a few weeks. Close orbital distances create a phenomenon called tidal locking, where one side of the planet always faces the star while the other side remains in perpetual darkness. The day side would experience an eternal noon with temperatures high enough to boil water, while the night side would be colder than Antarctica. Between these extremes lie the terminator zones, a twilight boundary where temperatures might allow for liquid water and possibly life. Colonies on tidally locked worlds would have to be built in this narrow strip where perpetual sunset provides enough warmth for human survival. Red dwarf planets face another challenge. These stars often produce powerful solar flares that can strip away planetary atmospheres over millions of years. However, planets with strong magnetic fields or dense atmospheres could resist this erosion and retain habitable conditions. The dim red light from these stars would require fundamental changes in any terrestrial agriculture. Plants would have to adapt to near-infrared wavelengths, creating alien forests that appear black to human eyes but efficiently collect the available starlight. Despite these challenges, red dwarf systems offer unprecedented stability. Once a red dwarf reaches its main sequence phase, it can burn stably for trillions of years without significant changes in brightness or energy output. Civilizations established around these stars could literally outlast the universe as we know it. Future human colonies around red dwarfs may evolve into something unrecognizable to modern humans. With trillions of years for evolution and adaptation, these distant descendants could become the ultimate survivors, the last intelligent beings in a universe growing cold and dark. By the time red dwarfs begin to dim and die, Earth's descendants may have learned to harness energy sources beyond stellar fusion, ensuring the survival of consciousness long after the last natural star has faded. But not all worlds orbit stars. Some planets wander through the cosmic darkness alone, carrying their own mysterious possibilities. Drifting in the boundless darkness between star clusters, there exist worlds devoid of a central star, ejected from their parent systems. These cosmic orphans wander the galaxy, carrying hidden oceans deep beneath thick frozen shells. Rogue planets, also known as free-floating planets, reside in interstellar space, not orbiting any star. These wandering worlds were either expelled from their original solar systems during turbulent, chaotic periods of their formation, or they originated independently in the dark clouds between stars. Astronomers hypothesize that our galaxy contains billions or even trillions of rogue planets, potentially outnumbering stellar worlds by hundreds or even thousands of times. These invisible wanderers drift through space at tens of miles per second, following the galaxy's unseen gravitational currents on journeys lasting billions of years. Imagine rogue planets as vast cosmic icebergs, silently floating in the boundless ocean of darkness. Deprived of a star's heat, their surfaces freeze to temperatures near absolute zero. Any atmosphere they once possessed would condense and fall as snow, forming landscapes of frozen nitrogen, oxygen, and carbon dioxide under a sky as black as the void itself. However, beneath these icy surfaces, some rogue planets may harbor conditions potentially suitable for supporting life. Planets with dense atmospheres or significant radioactive decay in their cores could sustain liquid oceans, sheltered beneath miles of ice. These hidden seas could remain warm for billions of years, deriving energy not from starlight, but from geothermal sources. Rogue planets similar in characteristics to Jupiter could generate enough internal heat through gravitational compression to keep vast oceans liquid for longer than the current age of the universe. These wandering water worlds could support complex ecosystems based on chemosynthesis rather than photosynthesis, similar to the unique life forms inhabiting deep-sea hydrothermal vents on Earth. Some rogue planets may have been ejected from their home systems along with their captured moons. A large rogue planet with several satellites could maintain a complex gravitational system in interstellar space, with tidal heating keeping the moons geologically active and potentially habitable for billions of years. Detecting rogue planets presents enormous difficulties because they emit virtually no light and can only be found by their gravitational effects. Astronomers use a method known as gravitational microlensing, where the gravity of a rogue planet briefly magnifies the light from a background star as it passes between the star and Earth. Recent scientific research indicates that rogue planets may be surprisingly widespread. Some estimates suggest that for every star in the galaxy, there may be 2 or even more free-floating planets wandering in the interstellar medium. This would mean the existence of trillions of hidden worlds, invisibly drifting in the cosmic darkness. Advanced civilizations could deliberately eject planets from their home systems, using this as a form of cosmic colonization, giving worlds a precisely calculated gravitational boost. They could send habitable planets on interstellar journeys lasting millions of years, spreading life throughout the galaxy on a much longer timescale than modern spacecraft travel. Rogue planets could act as stepping stones for interstellar exploration. Instead of making a full journey to another star system in one leap, spacecraft could move between rogue planets, using them as refueling stations and waypoints for significantly longer journeys. Some rogue planets might retain dense atmospheres heated by radioactive decay, creating powerful greenhouse effects that keep their surfaces warm despite a complete lack of stellar heating. These worlds could potentially support surface life, powered by geothermal energy rather than sunlight. The discovery of habitable worlds wandering in interstellar space would fundamentally change our understanding of potential locations for life. Instead of being limited to narrow so-called habitable zones around stars, life might be able to thrive throughout the boundless galaxy, in the dark, immense expanses located between star systems. For humanity, looking to the distant future, rogue planets present both enticing opportunities and serious challenges. They can offer both valuable resources and habitable conditions for those who dare to venture into interstellar wanderings. However, they also serve as a stark reminder that the overwhelming majority of galactic real estate resides in chilling darkness, far from the life-giving light of stars. As we contemplate spreading beyond our solar system, we must prepare to encounter a universe where most potentially habitable worlds wander in eternal night, warmed only by the internal heat of their own formation and the slow, relentless decay of radioactive elements deeply hidden in their cores. But even the longest-lived stars and the most stable rogue planets cannot escape the ultimate fate reserved for all energy in the cosmos. In approximately 13.8 billion years, when the last star fades and the last black hole evaporates, the universe will reach a state of maximum entropy. At this point, no work can be done, and time itself will lose its meaning. The heat death of the universe stands as the ultimate deadline for all intelligent beings. According to the fundamental laws of thermodynamics, energy continuously moves from hot to cold. This process cannot be reversed without an external input of additional energy. Eventually, the universe will reach thermal equilibrium, where any energy gradients necessary to power stars, planets, or life will vanish. This cosmic endgame unfolds on timescales that defy human comprehension. In about 5 billion years, our sun will exhaust its hydrogen fuel and expand into a red giant, boiling away Earth's oceans and atmosphere. However, these are merely the opening chords of a grand symphony of destruction that will play out over trillions and trillions of years. Imagine the universe as a giant mainspring, wound during the Big Bang and relentlessly unwinding ever since. The expansion of space, the formation of galaxies, the birth and death of stars, All these processes represent a continuous flow of energy, from concentrated forms to dispersed ones, steadily bringing us closer to a final state of equilibrium. In approximately 100 trillion years, star formation will completely cease as galaxies exhaust their reserves of interstellar gas. The universe will enter a period that astronomers call the degenerate era, populated exclusively by white dwarfs, neutron stars, and black holes, slowly cooling in the ever-expanding darkness. But even these stellar remnants will not exist forever. Protons, the fundamental building blocks of ordinary matter, could theoretically decay with a half-life of approximately 10 to 34 years. If this prediction proves true, all atoms will eventually decay, leaving behind only electrons, positrons, neutrinos, and photons in an ever-diluting cosmic soup. Black holes, the longest-lived objects in the universe, will exist significantly longer after proton decay. However, even they cannot escape the relentless laws of thermodynamics. Stephen Hawking discovered that black holes slowly evaporate, emitting radiation, with the most massive holes requiring approximately 10 to 100 years to completely disappear. The final era of the universe will be characterized by the dominance of increasingly sparse gas of elementary particles and photons, whose temperatures will approach absolute zero. No complex structures can exist in such an environment. No chemistry, no biology, no consciousness, only elementary particles drifting in an ever-expanding void. Nevertheless, some theoretical physicists propose hypothetical ways in which intelligence could survive even this ultimate catastrophe. Advanced civilizations could potentially harness the energy released by proton decay or black hole evaporation to power incredibly efficient computational systems. These systems could sustain intelligent minds at such slowed rates that subjective time would stretch infinitely, even as the universe relentlessly cools. Other possible scenarios include vacuum decay, where the fundamental properties of space itself undergo catastrophic changes, or the Big Rip, where accelerating dark energy eventually tears apart molecules, atoms, and even elementary particles. Both of these prospects would end the existence of consciousness significantly faster than heat death, but based on current astronomical observations, they are considered less likely. Some prominent cosmologists deeply ponder cyclical models of the universe in which the current phase of expansion eventually reverses, leading to a big crunch capable of restarting the cosmic cycle. In such models, intelligence could find ways to encode information that can survive the transition from one universe to another. The heat death scenario assumes that the fundamental laws of physics as we understand them today remain unchanged throughout boundless cosmic time. But if consciousness can modify physical laws or discover entirely new energy sources, the ultimate fate of intelligence may differ significantly from what thermodynamics predicts. For humanity's immediate future, heat death provides a critically important perspective on our cosmic significance. We exist in a relatively short window of existence when the universe contains enough organized energy to sustain complex structures such as stars, planets, and life. Maximizing this unique opportunity may be our species' most important responsibility. However, the transition from a planetary to a cosmic civilization may be only the beginning of an even grander transformation. The choice facing humanity is simple, yet profound. Evolve into a cosmic civilization capable of surviving the death of stars or remain forever confined to a single world, awaiting inevitable extinction. To truly become a cosmic species requires far more than just building better rockets or developing faster propulsion systems. It demands a fundamental transformation of human consciousness, biology, and social organization. We must evolve from planetary beings into entities capable of thriving in environments that would instantly destroy any terrestrial organism. This grand transition will occur in stages, with each stage representing a quantum leap in our capabilities and cosmic perspective. First comes the mastery of our own solar system, establishing self-sustaining colonies on Mars, mining valuable resources from asteroids, and building rotating habitats in airless space. This initial phase could begin within the next century, provided we maintain our current pace of technological progress. Imagine this first phase as learning to walk before we can confidently run. We need to prove that humans can live and reproduce in space, develop closed-loop life support systems that function for decades, and create technologies to produce everything necessary using local space resources. The second phase involves reaching nearby star systems using whatever propulsion technology we can develop, be it generation ships, fusion rockets, or exotic physics we have yet to discover. The first interstellar colonies will mark humanity's transition from a single-world species to a multi-system civilization. But the true transformation occurs in the third phase, when human settlements become fully self-sufficient across multiple star systems. At this point, we achieve true cosmic redundancy. No single catastrophe, no matter how massive, can wipe out our species. We become immune to asteroid impacts, supervolcano eruptions, gamma-ray bursts, and even the death of our home star. This widely distributed civilization will need to develop entirely new forms of governance, economics, and communication adapted to the vast distances between worlds. A message sent from Earth to Proxima Centauri takes 4.25 years to arrive. Achieving consensus across interstellar distances requires extraordinary patience and planning on scales no human society has ever achieved. Advanced cosmic civilizations will likely bear little resemblance to modern humans. Through advancements in genetic engineering, the human body can be adapted to entirely different living conditions. Diverse gravity levels, aggressive radiation fields, and varied atmospheric compositions distinct from Earth's. Cybernetic modifications, in turn, will pave the way for seamless and direct interaction with complex spacecraft systems. Moreover, the concept of digital consciousness may provide an opportunity for exploring and colonizing environments that are inherently too dangerous and unsuitable for the existence of biological life forms. The energy needs of a truly cosmic civilization far exceed anything modern humanity can imagine. The realization of such grandiose projects as the construction of Dyson spheres, capable of completely encompassing a star and harvesting its energy, or the acceleration of colossal generation ships to significant fractions of the speed of light, as well as the large-scale terraforming of entire planetary bodies, require energy sources comparable in power to stars. Thus, mastering controlled nuclear fusion, utilizing antimatter, or developing entirely new exotic energy sources becomes an imperative condition for implementing ambitious projects of cosmic scale. Perhaps the most significant aspect of becoming a cosmic species is taking on the colossal responsibility for the preservation and subsequent spread of life throughout the universe. There is a possibility that humanity is the only intelligent species in its immediate cosmic vicinity, which places upon it the role of guardian and perpetuator of billions of years of evolutionary development. It is upon humanity's ability to expand and settle that the very existence of intelligence and its potential to thrive among countless stars may depend. The alternative scenario, conversely, is quite sobering. Every biological species that remains confined to the limits of a single planet inevitably faces the threat of complete extinction. Stars, in the end, fade. Planets eventually become uninhabitable, and unpredictable cosmic catastrophes can erase many epochs of evolutionary development. Without mastering spaceflight and settling on other worlds, the very existence of consciousness may prove to be no more than a fleeting glimmer in a lifeless and indifferent universe. However, if humanity succeeds in spreading beyond its home planet Earth, it has a chance to become something truly unprecedented in the annals of cosmic history, a species capable of surviving even the stars themselves. Its descendants will be able to directly witness the grandiose processes of the formation and destruction of entire galaxies, guide the evolutionary development of life on a cosmic scale, and perhaps even exist after the heat death of the universe itself. The transition from a planetary civilization to a cosmic one marks the next, truly great chapter in human evolution. Humanity stands on the threshold of this monumental transformation, already possessing the necessary technologies to initiate serious interstellar exploration within a single human lifetime. Thus, The key question is not whether it is capable of leaving the confines of its solar system. The main question is whether it will have the wisdom and unwavering determination to become truly worthy of the boundless expanse of the stars. Friends, thank you for your attention to our work. If you haven't subscribed to the channel yet, now is the time. See you in the next video. Goodbye for now.